Hey, Algebra, Lesson 18, expressed in different ways. We're going to do a little bit of review of some skills that you guys learned in pre-algebra, just to refresh your memories, okay? So, if you remember this, it's going to be a great way for you to chill and refresh your memories. If you don't, it's a great opportunity for you to relearn it. And really dive in and practice some skills that are quite necessary for success in algebra. So first, let's decide if each are equal to 1.21 raised to the 100th power. In lesson 17, I reminded you of powers raised to powers and what you do mathematically with those. So when you have a power raised to a power, you multiply the two powers and you get that. Now when I have, let's say, I had to sneeze. When I'm multiplying variables raised to powers, I actually add the exponents here. So if I look at this first one, I have a power raised to a power. Okay, what I do with a power raised to a power is I multiply those two, which gives me 1.21 raised to 100. Okay, here I have a power raised to a power again, so I need to multiply those, which would be, 50 times 50, which is 1.21 raised to the 250. Okay, so this first one is equivalent, the second one is not. Here, power raised to a power again, but it's 1.1 raised to the 200. What is 1.1 squared? Yep, I'm going to erase that and show you something else. So if I actually change colors here, square this first, 1.1 squared is 1.21 raised to the 100. So that is equivalent. And here, pretty cool, I don't know why I didn't change pens, I can make that raised to the 2 raised to the 100, because when I multiply these, I get 200, right? And 1.1 squared is 1.21 raised to the 100, so that is equivalent. So this one right here is the only one that is not equivalent. All right, population projections from 1790 to 1860. The United States population in thousands is modeled by the equation given here. T is the number of years since 1790. But how many people were living in the United States in 1790? So in 1790, that's year 0. So I would raise it to the 0. Sorry, I don't know why I'm still in red. 4,000, 1.031 raised to the 0. That wipes this all out to 1, because anything raised to the 0 power is 1. And I get 4,000, which in thousands, so it's 4,000,000, or 4 million. Now, 1860, that would be 70 years since 1790. 4,000, 1.031 raised to the, 70. And that's going to be about 33,897,000. Yep, so quite a bit more. I put the zeros in there and the commas so that I can visually see which number is bigger a little easier. As I said, math teachers can be a little bit lazy, so I do things to make my life easier. Commas make my life easier. What is the approximate annual percentage increase predicted by this model? If you look at this value, 1.031, the 0.031 is the increase. I move my decimal over and it's 3.1% is my annual percent increase. Part C, what does the model predict for the population in 2017? This is going to be funny. So year 2017, how far is that after year 1790? Do a little bit of math, and that is 227 years. So let's put it in the equation. 4,000, 1.031 raised to the 227. I get 4090505.78. So that should be 6. And then 3 zeros. Put my commas in. That's 4 billion. Do you guys think that's accurate? 4 billion? I'm thinking not, right? Population for growth in the U.S. Is not at the same rate. As we said, things that are exponentially growing, they have to level out at some point because the Earth can't sustain that many people. The United States can't sustain that many people. Okay, cool. Number 2, what percent increase does the model predict each decade? Explain. So we go back to that, what we did in number 1, if we just talk about the decades, I'm at 1.031 raised to the 10th power. Handy dandy calculator. If I look at that 1.031 raised to the 10th power, I'm at 1.357. And if I think about, like, that is the percent increase with the 1, okay, this right here is my new percent increase with the 1 as it's going back to 100%. So 35.7% increase would be my answer for part A. Part B, suppose D represents the number of decades since 1790. Write an equation for P in terms of D, modeling the population in the U.S. So we already know P equals 4,000, 1.031, and that would be raised to the 10. If I put that in terms of D, I'm going to put a D up here because the D would represent each decade. So 1 decade, if D were 1, it would be 1.031 raised to the 10th power. If it were 2 decades, I would have 1.031 raised to the 10th power raised to the 2nd power, which is just 1.031 raised to the 20th power, like 2 decades would be. Number 3, what percent increase does the model predict each century? So I would have a 1.031 raised to the 100, because that would be a century is 100 years. Handy dandy calculator. Raised to the 100. I get 21.177. Okay, accounting for the, like here we said this was our percent increase because this accounts for the 100%, the beginning, the full. How do I account for this? Because I don't have a 1 point something. So I need to account for the 100% that we begin with. So for here, I subtract 1, and that's how I get 0.031 is my factor. Okay, here I do the same thing. I subtract 1, and this is my factor. Okay, so it is increases by a factor of 20, which is huge. Okay, that would be 200 and roughly 18% increase. Sorry, 2018% increase, which is truly crazy. That was part A. I didn't leave a lot of space for part B, did I? Suppose C represents the number of centuries since 1790. Write an equation in terms, equation for P in terms of C. I'm going to raise that to the 100 raised to the C, just like we did for the decade. Okay. I could also change that to 20.18 to the C to account for the 1.031 raised to the 100. All I did there was 1.031 raised to the 100, subtracted that 1 of original, and get something without the 100 to the power of 100 in there. So, all right. Okay. One more example. Interest calculations. So in the previous example, we saw that there are different ways to express the same exponential growth pattern. We did decades, we did years, we did decades, we did centuries. So here we're going to identify and interpret expressions that represent different compound interest situations. So here are three expressions and 3 descriptions. In each case, $1,000 has been put in an interest-bearing bank account. No withdrawals or other deposits, aside from the interest earned, are made for 6 years. It's going to give you 12 times 6 is 72. I don't know why I'm still in red pen. Sort the expressions that represent the same amount of interest into groups. One group contains more than 2 expressions. One of the descriptions does not have a match. Write an expression that matches it. Okay? So let's read through these descriptions. I have 7% annual interest compounded semi-annually. 7% annual interest compounded monthly. 7% interest compounded every 2 months. Okay, this is the one we've done a little bit more of. So let's look at this. 7% annual interest compounded monthly. And we said that we're doing this for 6 years. So monthly for 6 years would be 72. So I believe that would be this one. I do see that our 7% interest rate holds for each one of these problems. That got a little messy, so I'm going to erase that. But we do see that. We have the same interest rate for each problem. The only thing we're really comparing is the power. Okay, so we have that one. If we also look at that one, I have compounded monthly for 6 years. And if you remember, a power to a power, if I have x raised to the 12th power raised to the 6th power, it's the same as x raised to the 72nd power. So the first and the third expression all go to that 7% annual interest compounded monthly. So this second expression here, I'm going to use some blue. That is an example of 7% annual interest compounded semi-annually. Semi-annually, okay, would be twice a year for 12 months. Okay, where, change back to a black pen, here, annually for 6 years. Go back to here, we're compounding it semi-annually, which is twice a year. Okay, so that would be an example of that one. That's a stretch, okay? That's something that you guys have never really thought through or worked through before. So that blue one is a little different. Okay, we're going to get through some more of these to practice, but here's just our first taste of this type of problem. So the last thing that we were supposed to do is write an expression for this last one. Let me get a green pen out. 7% annual interest compounded every 2 months. Okay, so if we're compounding it every 2 months, we're really breaking that into 6, which means we're going to raise it to, we don't want 72, but we're going to compound it half the amount of time, which is 36. Okay, so that would be compounding every 2 months for 6 years. So every 2 months would be your compounding it 6 times. In a year, 36 times overall, because that would be for 6 years. Okay, again, it's kind of a stretch, the blue and the green one. And that's actually all we have for today. We're going to practice that. If you get to a homework problem on that one and you're stuck, please go ahead and message me, okay? And we will figure it out. All right, just go to that Google Chats, Google Hangout. I always miss the word that I'm supposed to be using, but if you can't reach me, email. But that Google Hangout seems to be working really well.